We now have Dr. B.K. Handique, Scientist Engineer ASAP, Northeastern Space Application Center, who would be delivering his expert talk on UAV remote sensing for hill agriculture scope and challenges. Dr. Handique has more than 18 years of experience in space technology application and research in agriculture and has been leading a national program on application of remote sensing and GIS in sericultural development. The project was awarded National e-Governance Award in the category of Innovative Use of GIS e-Governance by Department of Administrative Reforms and Public Grievances, Government of India. I welcome you, sir.
Yeah, thank you. I think hope I'm audible.
Yes, sir, you're audible.
So first, I would like to thank Dr. Alok Mukherjee from Let's Connect and BIT Mesra for giving me the opportunity to share my views and thoughts on the topic of UAV remote sensing. So I'll be basically focusing on the relevance of UAV remote sensing for heat agriculture. So I hope I'll share my screen and hope it will be visible to all of you. So I hope all the audience, the participants who are participating in this national seminar workshop on application of space technology and artificial intelligence for climate resilient agriculture and disaster management. So they are acquainted with, if not UAV remote sensing, but the satellite remote sensing and the different applications that satellite remote sensing we have in different thematic areas, maybe like agriculture, forestry, water resources, urban planning, and so forth. So here, what I have brought the topic, because as we know, satellite remote sensing has been there for different thematic applications. Then in the recent times, UAV remote sensing has emerged as a complementary to satellite remote sensing. And then more than the plain or valley areas, we have even more challenges. Not the challenges, but even the requirements are many in terms of UAV remote sensing. That is the reason why I brought the topic UAV remote sensing and taking and focusing on the topic that while we are aiming at climate resilient agriculture and disaster management support using space-bound observations. So in that perspective, I would like to share some of these our experiences, what we have been doing, and also we are continuing and planning to do. So that is what I'm going to share with all of you. Can I go to the next slide? Yeah. So as all of you must be aware of the fact that hill agriculture, when you talk of the entire country, we have, even though we have around 20% of areas recognized as a hill, under hill state or hill stations category. So that, but out of that, only a part of it actually comes under agriculture. Agriculture including other allied areas like horticulture and sericulture, etc. So there, and this hill agriculture system actually support around 5% of the country's total populations. So that way, it is very important to support. And these areas, the hill agriculture, why it is important, because these areas are basically characterized by fragility, and there is a lot of inaccessibility, heterogeneity, ethnicity. Of course, these areas are having rich biodiversity. And then the physiographic and climatic conditions favors in these areas a wide range of field crops as well as horticultural crops. So that need to be seen, which are more important in terms of supporting the rural livelihood, the tribal livelihood, and also what is the potential of further expansion of these areas. Then in recent times, I think we have noticed that geospatial tools and techniques have found to be very critical in providing inputs for mapping, monitoring, and planning of these critical agricultural and horticultural resources. Now, so when we deal with the satellite remote sensing, so we are bound to encounter a number of challenges when we deal the hill agricultural systems. So I think photographs you might have observed. It is unlike that the agricultural systems what we have in valley areas or plain areas where there is a systematic cultivation, there is a monocropic pattern, there is a large areas under cultivation. So in that case, it is relatively easy to assess from the satellite-based observation or satellite remote sensing. But here what happened in case of field agriculture, where we have the undulating topography, the areas are not accessible, and then the very least percentage of area under cultivation is there. You have to look for like a small area, a small crop is grown within a forest area, so we need to look for. And then the terrace farming and zoom cultivation also add problem to effective identification or delineation of these crop areas. Then another characteristic is that the small and fragmented acres of field. So because of that, the existing resolution has its own limitation to detect all the smaller patches of agricultural fields. And then many of these areas, or most of these hilly areas, we have the persistent cloud cover, which hinder the optical remote sensing to detect and monitor the agricultural systems. And then also you might, or all of us, we might have experienced that the cropping pattern, the itself is like a mixed cropping pattern, because a number of crops are grown together, and then crops are grown in like a maybe sometimes intercropping or multi-stage or multi-story cropping systems. So which adds problem to the satellite remote sensing based observations. So that is where this UAV remote sensing has become more relevant in terms of identifying those smaller crop patches in hill areas and for their effective planning and monitoring. So now coming to the UAV remote sensing. So now we have a lot of options. So to suit different agricultural systems or monitoring different agricultural systems. So now one way that we can have, we can buy a ready-made UAV systems designed and developed by different companies, or indigenously we can build or design these UAV systems locally as per our requirement. So these slides I brought out because like at the Northeastern Space Application Center, we have a UAV laboratory where our engineers, they design as per our requirement so that the required the sensors or the camera systems, it can be mounted and can be fitted as per our requirement. So there may be different numbers of options. We can have quadcopter or hexacopter, different designs as per our requirement we can have. So now that we have a different UAV system, either we brought an integrated system or we develop our own, then next question comes the type of sensor or camera systems that we are going to fit, because it is very critical, because it will depend the type of applications which we are going to have. Suppose if we are going to only the map those areas under agriculture, the different agricultural systems, a simple RGB camera system may be enough. But if we are going for observe the interfield variation or within field variations, or to measure different biophysical parameters of the crops, so in that case, so we have to go for different sensor system, maybe with a multispectral camera system or even a hyperspectral camera system. So here I have just shown 3 camera systems what we are having here. The first one is a 5-band multispectral camera system, 𝐸𝐸𝐴, got by the 𝐸𝐸𝐴 company. Second one is that I think it is a Parrot this 4-band multispectral sensor. Down there it is a very high-end hyperspectral camera sensor. Of course, this testing we are doing for this hyperspectral sensor. So where we assume a lot of applications in terms of identifying or analyzing the biophysical parameters of crops and its relations to different climate variables. Now, coming to the real applications of UAV. So first thing is, what is very important is the flight planning and the data acquisitions. So for that, what is important that to identify the area, to see all parameters in terms of physiography, like elevation, slope, because so we have different systems, like it can be as per the terrain, we can plan the flight mission. Here, based on the height of the flight, the type of resolution. So normally here we call in terms of UAV, we call GSDs. This is ground sampling distance. Like based on the height, because we have it down there, I think you might have seen the GSD, it depends on the pixel size and the flight altitude and the focal point of the camera. So there, so we define a very specific flight height, so that to get a specific ground sampling distance, like here, like 8 centimeter when you flight like a 120 meter height, then approximately we get around 8 centimeter kind of GSD, or we can say spatial resolution for that particular UAV flight. So the flight planning is very important, and here what we can do before going to the actual flight, we actually plan in advance, taking the coordinate even directly from the Google image. Also, if we have a KML file, we can plan the entire flight, how much time it will be taking, because these UAVs, as you all know, it is supported by battery, which has a limited time period. So within that time period, how much area we can cover. So what will be the overlapping we'll be giving, because here it is very important to give a very high overlapping, both forward and sidewise. Like we used to give around 75% overlap, forward overlapping, and 60% sideways overlap, to have a very good tie punch 3D point generations. So that is why it is important, and because of this maximum overlapping, so the time requirement for the flight is more in case of UAV, unlike satellite. So now, once we do the flight, so then the data will be captured. And one thing we have to remember that, so because the resolution is very high resolution, the images will be captured, and that will lead to very high data volume. So we should have a mechanism or the storage capability to store the large volume of data. Suppose for a 20-minute flight of this RGB camera system, we'll be having around 1,000 to 1,200 images. So that images need to be stitched together. Of course, this because of this onboard GPS systems. So normally we don't have much problem in terms of stitching or the georeferencing of all those images. So the software normally it takes care the stitching of the images, but the computer system should be having enough processing power to stitch or mosaic a large volume of data set. That is important. So once we have, then we will be creating a 3D surface of terrain models, and then once we go for the process, and that will be resulting in a very high resolution orthomosaic images. And down there, I think one image I'm showing here, what you can see here, and like this is an image, even though it looks like here it is a 2D image. Yeah. So once we can have a 3D model, because we have a very high both forward and side overlapping. We can create a 3D model. So now this you can see is a typical hill agriculture system. So if you see only from a 2D perspective, so it altogether gives a different perception. But when you model it, or when you see in the 3D perspective, so you can see like because the crops are grown at different height. So here you can see, so here like a maize crop is there, then pineapple is there. So here is the maize field within a field. So of course this is a draft over the DM, so it's not the original image, but this what it gives a complete perception, 3D perception of the entire terrain, so that we can plant, we can identify the crop at different height, and then when we'll be processing further, so then we can take care of the different aspect in terms of slope or in terms of heights. Now, coming to the data processing, so we have different options. Either we can have the available page softwares, like we have Pix4D, we have AZSoft. There are many softwares are there. And what I brought this slide here is just to emphasize that because many of the time, if we cannot afford to have the page softwares, so even there are many open source tools are available nowadays, for UAV data processing, and many of these scientists, they take advantage of these scripts and they modify and they develop upon it. So that helps in processing a large volume of data by different users, because what happened, we may not be having, or we cannot have such a high-end system for all the different users or all the students or researchers who are working on the UAV images. But these kind of open source tools will help them to process simultaneously or to experiment on these UAV images together or simultaneously. So there are different the scripts are there. Some of them I just brought here to show you all. Now, just the systematic steps that are required to process the UAV image. As I told you, flight planning is very important, where we'll be taking care of the flight height. We take care of the GSDs and then the overlappings and other required details. Then next steps comes in the feature detection or feature matching. Because of that reason, so we have given this very high overlapping both sides, so that we can identify a very large number of common features in the overlapping images. That will help us in generation of the 3D point clouds. And then we'll be generating that 3D surface construction with a meshing. And then this DSM and DM model will be generated. And then once we grab the images, then the orthomosaic images will be ready for further processing. So we can go for different generation of indices or generation of extraction of different features. Basically, in general, so these are the basic steps that are required to follow to make the image suitable for different classification or different applications. So now I'll be coming for some applications just to show like how this UAV has been useful in very high resolution mapping even at the farm level. So here one example I brought this is one village. So even though it looks very small, so this image is having more than 2,000 images stitched together. Okay, so this images, of course, here RGB image I'm showing here. So once we have that kind of image, you can just zoom in. It is a small section of that image, so you can see the type of details that are available. So this image, the flight was about 100 meters above the surface, and then once we have that much of detail, then you can see how difficult the classification will be, because the interpixel variability will be very high, and then because of that, we cannot run a direct classification like we do in case of satellite images. So normally here what we do, first level, we go for a kind of a segmentation of this object-based classification, object-based delineation or cluster-based approach. So now here also we may have a lot of options how we do the segmentations, and then the segmentation parameter may be different. We can give, as some of you may be knowing, so we can give different weightage to the segmentation parameters. Like we can give more weightage to the texture, or we can give more weightage to the color. So that weightage we can define, and based on the type of applications, so the first level segmentation will be done. Then once the segmentation will be done, then the image we bring it to 4 different type of classification. Again here, like different advanced classification techniques are there, so which we can apply, and based on our type of applications, so we can compare the result and see how best we can identify or delineate the crops at the field level. So that is the kind of variations we used to have in case of UAV image. So you can see like a different crops, like maize is there, tomato, cabbage, cauliflower. So once we have a mixed cropping, so then it is the challenge to use the kind of algorithm, so which will be able to best classify those classes or the crops. So here then the different options are there, and the different classification algorithm we can do a lot of trial and error. Then it has to also need to be supported with a lot of garden verifications and count measurements. Of course, this is identification. If we want to take the biophysical parameters or measure the biophysical parameters for the different crops, so definitely we have to install the required instrument in the field observation at the time of the flight, and then the corresponding measurement has to be taken, analyze the field, and then try to correlate with the UAV image. And then this is how, why I have shown these 2 images, because here to the 2 level of classification we have done. The first classification, if you see, only just to try to identify from the segmentation, we try to identify at the different land use level, like agriculture, horticulture, fallow land, forest. So that is where it may be relatively easy, where we can have a very good accuracy. Suppose here what I'm showing, that overall accuracy more than 90%, that can be achieved. But moment we go down for the delineation of individual crop, or identify the within field or infield variations, then that we have to really look at the kind of accuracy, what can be achieved, or what kind of acceptable accuracy we can get. So that is very important. Of course, for that we need to have a lot of trial and error. So here one more example, like so here also you have seen. So now what happened in 𝐸𝐸𝐴 many of the time, the crops are grown like a nearby house, or the kitchen garden. Many of the crops are grown. But this identification of these crops is very important. But officially, we may not have any records of them. So when you go for the precision farming or the very village level planning, so there it becomes important to identify even the crops in the kitchen garden. So how best we can use the UAVs or UAV remote sensing to identify those small pockets of crops. So here one example you have seen. So trying to develop or using different indices, so we can see how best we can identify crop. So anyway, it is again like the measurement or the scatter plot what we used to have in case of satellite remote sensing. Similarly, we can see so what best then combination can be best to detect the kind of crops at the field level or plot level. So that can be experimented. So here one example I brought, like how the UAV remote sensing is been helping in terms of assessing both the biotic and abiotic crop stage or crop damage assessment. So I think which is aptly justify the topic of the seminar. So how does this geospatial technology can be used to address all this, or to assessment of the crop damage. So here one example what I'm giving here, this is the rice field which was suddenly affected by plant brown topper, so what is called BPH. So as you know, this once it is BPH infested, it quickly spread the entire area, and the entire crop field may be lost due to this kind of infestation. So in that case, what happened? We may not have options other than the UAV remote sensing to quickly deploy and then make a quick assessment of the area damage and take the appropriate intervention measures. So this is one example from the Morigaon district of Assam, so where the crops were damaged, and then the Department of Agriculture approached us to quickly assess and the extent of damage so that they can take appropriate measure to control it. So we have deployed the image, and then you can see, like, can I have the fly? So the kind of detail what we can observe. So just I want to give you a feel. So here you can see the type of details that are available, and the crop area which are affected or infested by the plant brown topper. You can see it is like we call hopper burn, means that entire rice get burned because of this infestation. So left side image, I think you have observed the left side of the image. This is the affected areas of the crop. And then quickly the entire area can be surveyed deploying the UAV, and we can see the detail, what is the extent of damage and where it is happening, how quickly it is getting spread. So once we make that assessment, and it becomes easy to provide the report. And another thing I want to mention here, that this kind of assessment actually really help in the claiming of crop insurance. Because as you know, Government of India also giving a lot of emphasis on using UAVs for the crop insurance, or in the program of Pradhan Mantri Fasal Bima Yojana. So where it becomes very important to quickly make an assessment of the damage. Sometimes the damage may be because of the flood, because of the pest infestation, because of the hailstorms, but we cannot wait till the satellite passed over the areas. And sometimes it may be hampered, maybe due to the cloud and other issues. But here the UAV remote sensing really helps to quickly deploy and make an assessment, and this will really justify the claim for those areas affected due to biotic or abiotic infestations. So here I think you can get a feeling the kind of detailed information we'll be able to have using the UAV-based camera systems. So, and the statistics and all detail you can always generate, and that can provide very good information to the concerned authorities. So similarly, this is one example, like this flood damage in the Majuli Island in Assam. So there also what happened, because during the monsoon period, it becomes difficult to get the optical image. But flood is a perennial problem. So many of the time that the embankment get breached due to flood, and a large amount of crop area get damaged. So then it becomes very important to quickly make an assessment. And here, this kind of experiment we made an assessment how much area actually lost due to the flood inundation, and provided the report to the concerned authorities. Then coming to the observing the infill variations or to monitor different biotic and abiotic stress. So here we can see here the example shows the different maize crop grown in experimental plot approach. So here the observations were there, the different levels of treatments, like fertilizer treatments were provided, and because of this deficiency of different nutrients, the kind of the symptoms the crops will have. So that can be very well detected with the UAV remote sensing. And then if we can establish the relationship with the ground-based observation, so that helps us really to observe and monitor the plot level, and then we can suggest the suitable recommendations and to take appropriate intervention measures. So there may be different abiotic and biotic states. So here is some example I'm giving, and then so again there are a lot of R&Ds works are available, and a lot of experiments people used to conduct to how best we can detect these anomalies in terms of biotic and abiotic stress with this UAV-based sensors, and how accurately we can classify or delineate all those affected areas, so that quickly we can suggest the intervention measures. So it's in here, like we can have different indices just for your visualization. So again, we have different algorithms. Here also I would like to say that now the researchers are, of course, like these techniques even now become standardized, like SVM, support vector machine, random forest. So all these classification techniques are there, even though people are even working more on, because this is a small experimental plot, but when we need to deal large volume of data, then the big data analytics has a big role to play here to quickly make an assessment and quickly generate the classified output. So now coming to the advanced sensor system, of course, what I was previously showing now, like a 4-band, 5-band kind of system. So here I am coming that now with the time we are having, availability of more bands are available. Even in this case, like a multispectral, 10-band multispectral bands are available. So here I have given a table to compare the bands what we deal in a Landsat satellite image or a satellite image versus the sensors now currently available it has to use mount with UAV. So we can see the kind of bands we have. That means we have more tools to use in UAV to observe the minor details of crop variation or infill variations. So here the 10 bands that I have seen, even the radiate section. So some of you may be knowing that the radiate portion of the electromagnetic spectrum is very important for any vegetation studies, particularly the crops. So there is a definite jump in the reflectance pattern for all the crops, and this is the area even further divided, like in the radius area, there will be 3 bands we are getting in this sensor. So this will help us in minor, to identify the minor details or minor variation. Suppose within a crop, suppose it's a rice, but the varietal differentiation, or the crops which are grown at different time period, or the crops which are showing different the different root because of the different treatments in terms of fertilizer or other inputs. So that can be detected with this kind of these multispectral sensors. So recently we got this, and we have deployed and using and I just saw one recent experiment what we are conducting in the state of Gujarat, I think. Yeah, so here also this 10-band sensor we have mounted in a Trinity F90 Plus it is a fixed wing UAV, which has a long endurance time. It can fly almost 1 hour. So that we can cover a large area. Okay, one way we are covering a large area. At the same time, we are having 10 bin sensors. So that means we have a very good capability to cover a large area, to have a large number of observations. Can you just play? So just to give a feel, because it is unlike copter, this is just last week. We are conducting surveys in selected areas in Gujarat. So it takes a vertical takeoff, and then once we conduct a survey, then when we come back, then we can hold it. Either it is also like a vertical landing, and we can just hold it once it completes the survey. I think you can see. So you need not to fall on that, and slowly we can hold it. Yes. So that is how this advanced UAV system is working. And then but only thing we here the concern is that because we are having 10 bands data, we have a large volume of data. So then the processing capability is a real concern. We have to see how to process this large volume of data. Okay, this within 2 flights, I think 2 days of flight, we have got almost 1 TB data. So now the handling of this very massive data set is really a challenging one. Now, these are some of this data. Just quickly, I have downloaded and showing here. Like we can have, like you can see the infill variations, the kind of detail we can have for the crop observations. And then we, of course, at the same time, a lot of ground observations also have been taken. So which will be now used for modeling different aspects of these crops. So quickly here I'm showing, because that first, it is very important to observe all those spectral signatures of different crops in terms of crops, then the exposed soil, and then build the relationship. And then going for different classification approach, the advanced classification approach, to correctly identify or delineate those areas or observe all the details within the field. So now we have different experiments. Like this is one experiment I'm showing here. Like in hills, what happened? Like in many of the time, the area is inaccessible. I think here you can see we are making an experiment for irrigation. So that water is, of course, the bucket is there. Of course, it is a spray mechanism, not the irrigation. It is a spray for spraying the pesticide. So we can have the pesticide mounted on a UAV, and it can be well controlled in terms of spraying the volume and the area coverage, where we are going to precisely apply those fertilizer or pesticides. So now we also experimenting, like even in some hill areas, like when we have a kind of a zero tillage, here there even the planting or seeding also can be done with the UAVs. And then it can be done very precisely. We can maintain the row, we can maintain the distance. So which in a way will lead to the precision agriculture, even in case of hill agriculture. So there's a lot of experiments are there where we are conducting. But what we urge that many of the researchers who are interested in the UAV remote sensing, they can come forward to take different aspects of the UAV remote sensing in terms of payload, in terms of experiment, in terms of data processing, and there are different aspects to deal with. So I think with this, I just come to the conclusion saying that UAV remote sensing, as I think we have got a feel, that is a very powerful tool for the high resolution remote sensing, and that can provide very critical inputs at the individual farmers or plot level. So now I think we have seen enough of the satellite remote sensing, which is at a regional scale or district level. But what is really required to monitor and manage at the farmers level, where I think as of now, I think this UAV remote sensing can really help us or complement the satellite remote sensing. But what careful consideration is required is the flight planning, which I already told, it is very important. And the choice of sensors. Of course, it is an evolving area. A lot of sensors are being developed. Now we are having multispectral sensors. We are having hyperspectral sensor. Now we have leader sensors but processing of all those sensors and the corresponding field measurements is very, very important, because unless we able to really build a model fitting with the field-based observation with these aerial observations, so I think it will not going to lead very good inputs for the agriculture planning. So that is why it is very important to take a lot of ground measurements. This is some of these images I'm showing last week. This flight, what we are conducting in selected areas of Gujarat. So a lot of field measurements are being taken. So that will be integrated with the UAV-based observations. Then there are further requirements of advanced data processing. Anyway, this is also a very challenging and emerging area where a lot of people are working how best we can use in terms of the algorithm to handle large volume of data, because more the band, more the area coverage, definitely we understand the data volume. So to handle the data volume, it is required that we have very robust system in terms of computer processing or in terms of the algorithms. And then when we take all this field-based observation or the pilot measurements to make it operational or make it happen for the field level planning, so it is very important that there is a integrated approach required, and all the concerned stakeholders need to come forward to see not only the scientists who are working, not only the engineers who have developed, but also the users' requirement. We need to really see and identify the critical areas where it can play or it can give very valuable inputs for in terms of precision agriculture, or in terms of maximizing the agricultural production and minimizing the agricultural loss and damage whatsoever may be because of biotic stress, somatic stress, or the climate change. I think with this, I want to conclude. I thank all of you for patient hearing. Thank you all.